So this is page 97 in your notes. Example 1. Locate the stationary points on the curve y equals 5x to the power of 6 minus 12x to the power of 5 and determine their nature. Well, the first step I have to do is find out where they are. So the stationary points lie at dy by dx is equal to 0. So the first thing I'll have to do is find dy by dx. Well, dy by dx in this case is 5 times 6 is 30, x to the power of 5. 12 times 5 is 60 minus 60 x to the power of 4. But I know the stationary points occur where dy by dx is equal to 0. Therefore, I'm interested in finding x values where 30x to the power of 5 minus 60x to the power of 4 is equal to 0. Well, in order to solve this, the first thing I want to do is factorise it. I can take 30 outside brackets and x to the power of 4. That would leave me x minus 2 here. That means for these two things to multiply together to give an answer of 0, either this is 0 or this is 0. So either 30x to the power of 4 is equal to 0 or x minus 2 is equal to 0. Well, the only way for this to work would be if x is 0, and in this case x must be 2. So the two stationary points occur at x coordinate 0 and x coordinate 2. Now, when x is equal to 0, if I substitute into the first equation, I work out that y is also equal to 0. So this is the coordinate 0, 0 for one of my stationary points. When x is 2, y is equal to 5 times 2 to the power of 6 minus 12 times 2 to the power of 5, which is negative 64. So the second stationary point is at the point 2 and negative 64. I now know where the stationary points are. I need to identify the nature of the stationary points. Well, the first method of doing this is to work out what d2y by dx squared is, the second differential. I know d2y by dx squared is going to be, well, if dy by dx is 30x to the power of 5, if I differentiate the second time, 5 times 30 is 150 x to the power of 4 minus 60 times 4 is 240 x cubed. So this is the second differential. So when x is equal to 2, we'll look at this one first. d2y by dx squared is equal to 150 times 2 to the power of 4 minus 240 times 2 to the power of 3. Now, if I can't tell initially, I can do that calculation. I can tell that this number is going to be bigger than this number, because this is going to be 150 times 2 to the power of 4 and 120 times 2 to the power of 4. So this answer is going to be greater than 0 or positive. Therefore, it's a minimum stationary point, or I could call it a turning point in this case because I know it's a turning point. Minimum turning point at 2, negative 64. I've determined the nature of the first of our turning points. Now I need to consider the second turning point when x equals 0. Well, when x equals 0, d2y by dx squared is equal to 150 times 0 to the power of 4 minus 240 times 0 cubed. Now, for the wise amongst us, 0 minus 0 equals 0. Therefore, we don't know. It could be any type of stationary point. So we need to use our initial method. So we know we've got stationary points between at 0 and 2, and these are the only two stationary points. So I want to consider coordinates on either side of 0. I'm going to consider values of x. I'm going to consider -1, 0, 1. I can't go as far as 2 because that's going to be a different turning point. So dy by dx. Well, when dy by dx, remember dy by dx, I'll write it again since we can't see the top of the page, is 30x to the power of 5 minus 60x to the power of 4. When x is -1, this will become minus 30, subtract 60, it's going to be negative. When x is equal to 0, dy by dx is equal to 0. When x is equal to 1, this will be 30 minus 60, which is also negative. Therefore, that means I can now tell that we don't have a maximum or a minimum turning point. Because these gradients are the same on either side of our stationary point, we have a point of inflection. At the coordinate 0, 0. And that's how we use both the second differential and identifying, comparing the gradients of the curve in order to enable us to determine the nature of stationary points.